This is part 2 of my lecture on arithmetic progressions. I'll quickly review the definition of arithmetic progressions, and then I'll uh, present several problems and their solutions. An arithmetic progression is an ordered list, sequence of numbers, such that the difference between any two adjacent terms is constant. So we have an example here, minus 3, 4, 11, 18. So the difference is 7. And in general, we define an arithmetic progression using this formula here. This a sub 1 is the first term. D is the difference between sequential terms. And then if you want the nth term, you can compute it from the first term plus n minus 1 times the difference between the sequential terms. And this is the equation for the summation of the first n terms. Okay, so I mentioned this in the first lecture, but I thought I would just go over it very quickly here for folks who skipped the first lecture on this topic. So here's our first problem in the second lecture. Find 3 distinct triangular numbers that form an arithmetic progression. And then an extra credit, can you find an infinite family of such triples? And if you're not familiar, I'm going to quickly go over what are triangular numbers. Maybe the picture is easiest to see here. They're basically numbers that you form by arranging dots in a triangular form. So the first triangular number is 1, then 3, then you add a row of 3 below the row of 2, and you get 6 for the third one. Then you put 4 again to what you had, and you get 10, and you can see how it progresses here. And then the general formula for the nth triangular number is n times n plus 1 over 2. Okay, so our problem is to find 3 distinct triangular numbers that form a progression. So we want to have the same difference between them. Now, obviously, they're not going to be in a row. They're not going to be one after another. There's going to have to be some gap in order to have this difference between them be the same so that we have an arithmetic progression. In terms of the first question, we just needed to find one example, and I have that displayed here. We take the third, sixth, and eighth triangular number, we get 6, 21, and 36, and the difference is 15. So that's one solution. In general, we have this solution here where we have these 3 triangular numbers, k times k minus 2, k times k minus 1, and k squared minus 1. And these will give us an arithmetic progression in each case. The first one here is if you take k equals 3 and plug it in here, you actually get this one here. Let's look at the second one. We put in k equals 4. We get 4 times 2 is 8. And this is 12. And this is 15. And then you just need to evaluate these, the 8th triangular number, the 12th and the 15th. And you get these numbers here. And then the difference is 42. And I just put down a couple more examples. Now, of course, the question is, how do we come up with this? I'm just kind of giving you the solution without any reasoning. So in the next few slides, we'll talk more about how you come up with these solutions here. On this slide, I give some justification for the formula I showed you on this previous slide. So consider triangular numbers in an arithmetic progression. So you have, say, t sub a followed by t sub b followed by t sub c, where the difference is the same. So in other words, t sub b minus t sub a is equal to t sub c minus t sub b. I multiply by 2 here just to get rid of the 1/2 in the formula. So if we work these out, and I showed you one here, if we take 2 times t sub b minus t sub a, and then the 2 cancels the 1/2, and you just get b times b plus 1 minus a times a plus 1. Then you multiply that out, and you get this. Then you collect the b squared and the a squared together, because we know we can factor this, and then the b and the minus a. Then we factor this as b minus a, b plus b minus a. Then we can factor out a b minus a, and you get b plus a plus 1. And then you could do the same thing. It's just different subscripts here, but you have basically the same format. So to find an infinite family, introduce parameters for the gaps in the indices. And this is where we have a bit of a guess. Let the gap before the middle term, the t sub b, be k, and that would let that equal b minus a. And the gap between the middle t sub b and the last term t sub c be c minus b, and let that equal k minus 1. That's where the guess is. We're assuming the gap here is k, and then it's just one less between t sub b and t sub c. And if this guess is wrong, we'll get a contradiction in our computations, but it turns out it's not wrong. The guess actually does work. So we have a, just rewriting this slightly, we have a equals b minus k, and we have c equals b plus k minus 1. Okay, so that's just from our guess here. And then we substitute these values in for a and b in this equation up here. So on the left side, we have b minus a, which is k, right? K is b minus a. And then you have a, which is b minus k, plus b plus 1. And then you can just expand this out or cancel out things. So you get 2b minus k plus 1. Then the k carries over. Then we make the substitutions onto the right side here. We have c minus b. We guessed that to be k minus 1. And then we substitute in, we have b. Then this c here is b plus k minus 1 plus 1. And then we just simplify this, and we get k minus 1 times 2b plus k. Okay, then we set this equal to this. And if our guess was wrong, we would get a contradiction in here, but we don't. So we just set these equal, then we multiply on both sides. We get this on the left and this on the right. I just made this bold just so you can see we're going to cancel this out. Then we just bring down this and this here. Then we take the k squared here and subtract it from this side. We add k to this side. We leave the minus 2b here. Then we divide by minus 2, and we get a solution for b. And then we just substitute in b for here to get a. And we get a equals k times k minus 2. And then we substitute in b for here into c, and we get k squared minus 1, which, as you recall, these values for a, b, and c are what we had in our solution from the previous slide. Okay, so that's sort of a justification. The guess worked out for us. I guess the way to describe this in a more positive light is you need to try different indice gaps to see what works. This was sort of the easiest one, to just assume a gap k, and then whatever you have between the middle term and the last term, t sub c, assume it's just one less, because after all, these triangular numbers get larger as you go further out. So you would assume the indice gap would be less, and it turns out if you assume it's just one less, it actually works out. Now, well, the next few slides I'll show you there's even more solutions than what we have here. We can vary what the gap is, and in terms of the indices. Of course, the difference between the triangular numbers needs to be the same to meet our requirements. There are infinitely many other families of solutions from the one we saw in the previous slide. The previous solution utilized the gap difference between the indices of 1, where the gap before the middle term was k, again we're referring to the indices, and the gap after was k minus 1. By generalizing this difference, we can find distinct families of solutions for every integer gap difference. So let indices a, b, and c be such that the triangular numbers t sub a, t sub b, t sub c are in an arithmetic progression. Let the first gap be p and the second gap be q, in other words, the gap between the indices. The condition for arithmetic progression simplifies too, and I'll prove this 2 slides after this, but if you just accept this for the moment, that this is the value for b, given that we're assuming an arithmetic progression, and given these values here, a, b, and c for the indices. So if we fix the difference between the gaps to be delta, so now it doesn't have to be 1, which it was for our first example previously, then we can substitute that in here for b. We also let p equal k and q equal k minus delta. That just comes from this difference here. So we plug all that in and we get p squared plus q squared. P minus q is delta, then 2 delta in the denominator. Then we put in k for p, so we get k squared. Then k minus delta for q. And then the other 2 terms, this and this, are as they were here. We multiply this out and we add it to k squared. So we get 2k squared minus 2 delta k plus delta squared minus delta divided by 2 delta. And then we just divide this into each of the terms. So this first one gives us k squared over delta. Here the 2 deltas cancel, we just get minus k. Then here we divide the delta into the both of these terms. Here we get delta minus 1 divided by 2. So let's look at some examples of where we take different values for delta and find out our values for a, b, and c, which in turn give us our arithmetic progression. I'll do that on the next slide. Let's look at a couple of examples using the formulas from the previous slide. We'll start with taking delta equals 2. Here we look for solutions where the gaps are k and k minus 2. So the difference between the gaps is 2. Substituting delta equals 2 into our formula for b, we get k squared over 2 minus k, and then this would just be 1/2. Get a common denominator of 2, and you get this in the numerator. That's k minus 1 squared. But we need to have b to being an integer, so that means k minus 1 squared has to be even, which means k must be an odd integer. And we also need to have k greater than or equal to 3, otherwise this will be negative. So k needs to be an odd integer greater than or equal to 3, and that'll give us a family of solutions. These are our corresponding solutions for a and c. It's b minus k, and then c is a b plus k minus delta, but that's 2. Okay, so we'll take one example. Let's try k equals 5. We get b, let's see, for k equals 5, this is 16, divided by 2 is 8. Then for a, it's just b minus k, so 8 minus 5, 3. And then c is 8 plus 5 minus 2 is 11. And you notice the gap between the indices for a and b is 5. And then between b and c, it's 3. So the difference in the gaps is 2. And then we can plug in our numbers into the triangular number formulas. So we have t sub 3 is 6, t sub 8 is 36, and t sub 11 is 66. And you notice the difference here is 30, and the difference here is 30. So we get another solution. Then here we're trying delta equals 3. Very similar procedure we'll go through. So we'll take our formula for b again, copied it here. We put in 3 for delta, so we get this. And for b to be an integer, we still have that requirement. K squared must be divisible by 3, which means k must be a multiple of 3. And since we want this to be positive, it's going to have to be the next multiple of 3 would be 6. So k has to be greater than or equal to 6. Any multiple of 3 greater than or equal to 6 will give us an integer for b. And then we just plugged it into the formulas. So we get, again, a is b minus k, and then c is the same formula, but we plug in 3 for delta, and we get this here. And then we could do an example. There's an infinite number of solutions, but we'll take the smallest one, k equals 6, and then b would be 36 squared, 6 squared, which is 36, divided by 3, minus k is 6 plus 1, so you get 12, minus 6 plus 1 is 7, then a is b, which we just computed to be 7, minus 6, that's 1, and then c is, from this formula here, it's 7 plus 6 minus 3, that's 10. And we plug those into our formula, so t sub 1, t sub 7 is 28, t sub 10 is 55. And so let's see, the difference is 27, and again it's 27. So yeah, this is yet another solution. Okay, so we've now found multiple infinite number of solutions, in this case here, in this case here, and we can pick different deltas. In order to analyze them, you need to make sure that you satisfy these requirements. The k terms need to be positive integers, and then b needs to be an integer. So if you try, I haven't tried it, if you try delta equals 4, you may get different conditions. I assume it may not work for some values of delta, but I haven't tested them all. So there's maybe something to explore to see what values of delta work out and which don't. That may or may not be a hard problem, but you may want to look at least a few more of them, like 4 and 5, and see what you come up with. Okay, so on the next slide, I'll derive this formula for b that I mentioned previously, and then we'll be done with my presentation of this particular problem. On this slide, I derived the formula for b that I mentioned several slides back. As we established previously for triangular numbers, t sub a, t sub b, t sub c, to form an arithmetic regression, we need to have this equality hold true. We'll just define generic numbers for the gaps between the indices. So we'll let p equal b minus a, which implies a can be written as b minus p. And then we let q equal the other gap, c minus b, which means that we can write c as b plus q. And then we'll work on both the left and the right side of these two equations with the intent of eliminating a and c from both sides, and then we'll solve for b. So we'll work with the left side first. We have b minus a, so that's p. Then we have a, which is b minus p. Then b and 1. Then I just simplified this inside here. It's 2b minus p plus 1. And then I multiplied p to get this. So now we only have a b and a p in our equation here. And then we work on the right side. So we have c minus b is q. Then we leave B alone, but then C is B plus Q, then plus 1, and we add the two B's together, multiply through by Q, and we get this here. And now we have the right side just having a B and a Q. And then we set this equal to this. Done here. Then we move the terms with a B in it to the left and all the other terms to the right. So we subtract this, and then we add P squared, subtract P. We get this here. Then we factor out a 2B from this left side. And the right side we just slightly rewrote is minus the quantity P minus Q. And then we divide both sides by 2 times P minus Q to solve for B. And we get this. And if you recall, that was the formula for B that we had from a few slides back. Okay, that's it for this problem. I have one more problem in this lecture, and I'll get to that on the next slide. So this is the last problem in this lesson. Find the smallest common difference, D, for an increasing arithmetic progression of positive integers that contains no perfect squares. And maybe just add one point here, not so much as a hint, but just a point that I didn't emphasize earlier. You notice I said increasing arithmetic progression. So I may have given the impression in this lecture and the previous one that they always increase, but the difference D could be negative, in which case you can go down and have a decreasing arithmetic progression. I didn't give any examples of that, and it's not the case here either, because I explicitly excluded that possibility by saying it's an increasing arithmetic progression, meaning that D is positive. Okay, so have a look at that, and then I'll give you the solution on the next several slides. On this slide and the next, I'm going to prove a theorem that we'll use to solve the problem. So here's our theorem. Let an arithmetic progression be given by, this is the standard format we've been using. So A is the first term, N is a whole number, positive whole number, and then D is the difference between the terms. The sequence S contains a perfect square, in other words, a whole number squared, if and only if A is a quadratic residue modulo D. All right, so this is kind of terminology that's a little bit advanced. We haven't seen that yet, but what that means is there exists a solution X to the congruence X squared congruent to A mod D. And make that even clearer, we have some X that satisfies this here. So these are the terms in the progression, the arithmetic progression. We're just saying if there's some X that satisfies this for some value N, then of course you have a perfect square in your progression, which is not what we want, right? Our problem was to find the smallest value of these such that you can't have a perfect square in your progression. But we'll need this theorem to kind of work through the details. So it's an if and only if, which means we need to prove it in two directions. So on this slide, I'll prove it in the forward direction. Assume the sequence S contains a perfect square. Then there exists some integer X and some positive non-negative integer N such that X squared equals A plus ND. That's what I set up here. Then consider this equation modulo D. So we just take this mod D, and of course this term here is 0 mod D, and you get X squared equals A mod D. So by definition, this means A is a quadratic residue of D. So this was pretty trivial going in this direction. Going in the other direction is a little bit more involved, and I'll do that on the next slide. So for the second half of the theorem, we assume A is a quadratic residue modulo D. By definition, the congruence x squared congruent to a mod d has a solution. Let x sub 0 be a particular integer solution such that x sub 0 squared is congruent to a mod d. Now from this, we can generate an infinite family of solutions using the modulus. Consider integers of the form x sub k equals x sub 0 plus kd, where k is an integer. Squaring the above expression, which I've done here, square this, then we'll have the x sub 0 squared, and then the other two terms have a d in it. We don't care so much about this other than it's an integer. So we get this x sub k squared is x sub 0 squared plus some integer multiple of d. Thus, for any integer k, we have x sub k squared is congruent to x sub 0 squared mod d, and we know that's congruent to a mod d from what we have up here. So continuing, this implies that x sub k squared can be written in the form a plus md for some integer m. That's just from this and this. We just want to prove that x sub k squared is actually in the sequence, our arithmetic progression. We only need to ensure that this m is greater than or equal to 0, which is equivalent to the x sub k squared being greater than or equal to a. Right, that comes from here and here. If you look at this and this, if you subtract the a from the x sub k squared, if you subtract a from that, and that equals md, and x sub k squared is greater than a, then of course the m would have to be greater than or equal to 0. But that's pretty easy to prove because x sub k squared is equal to x sub 0 plus kd squared, and that grows, and this is positive, this is squared, this grows without bound as k increases, so we can choose k sufficiently large such that this is greater than or equal to a. Thus, there exists a perfect square in the arithmetic progression S. Okay, so we'll go back to the actual solving the problem on the next slide. So let's look at the solution to our problem. Just to remind us, the problem is restated here. Find the smallest common difference d for an increasing arithmetic progression of positive integers that contains no perfect squares. So we'll take d equals 1 as our first case and check that, and we don't need the theorem actually to check this. For whatever value of a we take, we're going to hit perfect squares because the difference is only 1. So if you took a equals 10, obviously you're going to hit 10 squared. So the perfect square, that's going to be in the sequence. You're going to hit things even before that, like 7 squared and 8 squared and 9 squared, but this case doesn't work. The second case, if the difference is 2, there's two subcases. If a is even, then the square of an even number is also even, and that means you'll eventually, with the difference of 2, you're going to hit the square of whatever initial point you start with. You're going to hit other squares, but for sure you're going to hit the square of a. And then if a is odd, you have a similar argument because the square of an odd number, like 7, is also odd. And if you're going by steps of 2, and you start with 7, you're going to hit 49. And in general, if you start with an odd number, you're going to hit the square of that odd number going by increments of 2. So these two are out. For d equals 3, we will use our theorem, and we'll look at x squared mod congruent to a mod 3, and we'll see what the possible values are we can get for a. So if we take x equals 0, we get 0, and so that's congruent to 0 mod 3. If we take x equals 1, that's equal to 1, which is congruent to 1 mod 3, and x equals 2. 2 squared is 4, which is congruent to 1 mod 3. So you can never, if you take a equals 2, you never can find the solution x congruent to 2 mod 3. So that's the case where we have no perfect square in such a sequence, where you start with a equals a congruent to 2 mod 3. Let me point to it here. A equals congruent to 2 mod 3. So if you can start with 2 or 5 or 8 and so on, you'll never, and you go mod 3, so you go, your sequence has your d equal to 3. You're never going to hit a perfect square in that case. Okay, so that's the answer. The answer is d equals 3, and a would be 2, or a is 2 mod 3. And I have another way of showing this third case on the next slide, which is a little bit more direct. It doesn't involve the theorem that we proved on the previous slide, so we'll have a look at that. So let's prove the case d equals 3 another way. What we'll prove is there are no perfect squares of the form 3k plus 2, which is equivalent to saying that if you start with an initial value of a equals 2 mod 3 for our arithmetic progression and take d equals 3, then you're not going to hit any perfect squares. So any integer n can be one of three forms. It must be, I should say, in any one of three forms. 3m, 3m plus 1, 3m plus 2. If you go to 3m plus 3, you could just factor the 3 out and you have 3m. If you have 3m plus 4, you can get that into this form here, and so on. So these are the only three possibilities. So let's look at each one of these in terms of our n, our integer n, and see what form they could be in. So if m is of the form 3m and we square it, we get 9m squared, which can be written as 3 times 3m squared. So 3, this is of the form 3k. And if we have n is of the form 3m plus 1, we square it, we get 9m squared plus 6m plus 1. We can factor 3 out of the first two terms, and we get 3 times some integer plus 1. In other words, it's of the form 3k plus 1. And if we take the third form, 3m plus 2 squared, we get 9m squared plus 12m plus 4. We can just break the 4 into 3 and a 1, and then these first three terms have a factor of 3 in it. So you have 3 times an integer plus 1, so we get that also of the form 3k plus 1. So no matter what form n is of, when you square it, you get it either in the form 3k or 3k plus 1, but never 3k plus 2. So we've proven this here, which means if we take d equals 3 and a equals 2 mod 3, and any such arithmetic progression will not contain a perfect square. Okay, so that was the last problem in this lesson. I have another lesson coming up on relatively prime numbers. So in other words, two numbers that don't share any factors other than 1. And then I have 3 lectures on prime numbers, and I may have more lectures beyond that, but I haven't developed those yet.